Okay, so go ahead and get out that worksheet that we had. I'm just going to go through this worksheet. Basically, I'll draw some pictures, give you some examples of these different equations. Everything that's on this worksheet that is boxed in red, it will be on the AP equation sheet. Anything that is not boxed in red, that's required to be memorized, or at least know where you can derive it from. So we'll kind of go through that, and hopefully it'll make sense to you. So our first equation, which we started with, was force of gravity equals big G m1 m2 over r squared. That's two objects that are close together or far apart, and the force of gravity that's felt between them. Big G, that's a constant, obviously we know that, and these are the two masses and the distance between them. We can set this equal to two different things. We can set it equal to the basic force of gravity equation that we know, which is mass times gravity, or we can set it equal to the centripetal force equation, which is mass times centripetal acceleration. Now, these two are slightly different than each other. If we're dealing with this one and this one, we're dealing with like me standing on the earth, here I am, and the distance between the center of the earth and the center of me is the radius. That's me feeling the force of gravity, and then I have a gravitational acceleration because of that. These two, the second equation, again, I'm going to have a lot of arrows here. I kind of apologize for this, but this is how we described it in class. So if we have the force of gravity equation setting it equal to centripetal force, this would be like the sun at the center of the universe, and then a planet like the Earth going around the sun. And because that planet is in an orbit around there, you have a radius between these two objects, right? The distance between their centers. But if you think about it, it's basically the same thing as a ball on a string. Instead of having a tension force pulling that object toward the center, we have the force of gravity pulling the objects toward the center. But essentially that force of gravity is equal to the centripetal force. So that's what we're going to do with that. All right, so first we'll start with these top two equations, like me standing on the earth, and I'll show you what you can do with those. They together will make an equation down here, which is the equation G equals big G m over r squared, and I'll show you where that comes from. So basically we're setting these two things equal to each other. We're setting force of gravity equal to force of gravity, which seems silly, but it's big G m1 m2 all over r squared, sorry about that little mark there, is equal to m times g. Now, remember, this is the m and the g for me up here. This is this picture. So we have to determine what's the m1 and the m2. But if I think about the force of gravity on an object, like me, I'm mass 1, let's call me mass 1, that's the object standing, and then the mass 2 is the central body. So if I'm thinking mass 1 and mass 2 over here, on the left side of the equation, that's me and the earth that I'm standing on. But over here, the force that I'm feeling is the force on my mass times acceleration of gravity. So m1, the mass of the object standing on the central body, cancels out, and you're left with big G. m2 over r squared is equal to little g. But the m2 in this case is the central body. So I'm going to define that over here. M1 is the orbiting body, or whatever body is standing on the other one, and M2 is the central body. Just to keep those clear. So that's where this equation comes from. Ta-da! We derived it there. It's a simple one-step equation. The second type of problem is we have some central body and the other one orbiting a distance away from it. And from that equation, we're going to derive a new few set of equations, actually. The only one we're not going to derive, actually I'm going to jump to it here on the next page, is the potential energy equation. Potential energy equation is capital U equals U sub G, that's potential energy, gravitational potential energy, is equal to negative big G m1 m2 over r. Now, the one thing that you need to know about this is kind of random. It's a kind of a random equation. They'll specifically ask for the potential energy. It has units of joules. We haven't talked about that yet. It's always negative, and it doesn't have the r squared value. I'm also going to write Kepler's law, but I'll show you where this comes from. This is like if I'm comparing the Earth and Mars. orbiting around the sun. So it's two objects orbiting around the same central object, that would be the sun in this case. The period of object 1 over the period of object 2 squared is equal to the distance that object is from the central body divided by the distance the other object is from the central body cubed. Now we're actually going to see from somewhere over here in a second where that comes from. And then we're also going to see where the speed of the satellite equation comes from. But let's go back to the previous slide and set these two equations equal to each other. So again, we're doing this. We're setting the force of gravity equation equal to centripetal force. So basically, we're just summing the forces, this stuff up here. Centripetal force is equal to the force of gravity. Centripetal force is mass times centripetal acceleration. Now, there's a lot of places along the way on this derivation where we pull things out. So I kind of want you to see that. And then this is big G, M1, M2 over R squared. Now, what you notice is we don't have an M1 and an M2 over here. But think about it. What is this centripetal force? This is a centripetal force acting on the Earth. So over here, we just figure out what's what. So if we want, in this equation, based on our sun and earth example over here, again, more arrows, M1 is the, and actually let's just make it the same as what we have it up here. M1 is our orbiting body, that's the earth. M2 is our central body, that's the sun. So if we're talking about the centripetal force, the orbiting body is the earth, and that's object 1. So what happens right here is M1 cancels out. So we have centripetal acceleration is equal to big G M2, or the mass of the central body, divided by R squared. But this isn't overly helpful. What is sometimes helpful that they ask for is the speed. So let's determine the speed. That's actually going to be the last equation, the speed of a satellite. Now, the Earth is essentially a satellite around the sun, but we can also have the Earth with a satellite above its surface. So you got to think a little bit beyond like what a satellite can be. It's any object orbiting around another object. So we're going to replace what we know as centripetal acceleration, v squared over r, is equal to big G m2, again, knowing that m2 is my central body, over r squared. Now what happens here is one of our r's cancel out. So this r cancels out. Now this is where we're going to pull out what v is equal to. V is equal to square root of big G, square root of big G, push the button, M2 over R. Now I'm going to write that on my next equation page, which is down at the bottom, the speed of a satellite. This is the speed of a satellite. Now I'm going to be a little more specific. If I want to know the speed of a satellite around the Earth, it's big G, mass of the central body, which is mass of the Earth, all divided by r. Now, it's important that you know r is not just the radius of the Earth. R is the radius of the Earth plus the altitude of the satellite. Because they'll usually say a satellite is so far above the Earth's surface, you have to not only take, just like we showed back here on the previous slide, we have to take, like if I had a satellite out here floating around the Earth's surface, I have to take the radius of the Earth, and then I have to add the altitude of the satellite, how high it is above the Earth's surface. That's the r in this equation. All right, if we keep going with this equation, which is something important to do, so we have v equals square root of big G. Actually, I'm going to back up. Oh, how did I get that to erase? I'm going to do my magic. Hey, okay. I'm going to back up to v squared equals big G m2 over r. Now, v is equal to something. Remember, a velocity of an object that's circling around another object. Velocity is distance divided by time. The distance is 2 pi r. That's the circumference divided by t. So I'm going to plug that into v here. And I'm going to get 2 pi r over t all squared is equal to big G m2 over r. Now what I'm going to do with this is I'm going to write two equations. I'm going to write an equation for what is the period of an object that's rotating around another object. So they might say, what's the period of a satellite around the Earth? That's so much distance from the Earth. or so much distance above the Earth's surface. Or another thing that they sometimes will ask is, what's the radius? I'm going to solve for both of these. I'm going to solve for period, and I'm going to solve for radius, and we'll have two new equations. So I'm just going to square everything in here for pi squared r squared over t squared is equal to big G. Again, this is mass 2, which is the mass of the central body, over r. Cross multiply this, and I get 4 pi squared r cubed equals big G m2 t squared. Do you see from Kepler's law where the t is squared and where the r is cubed? So that kind of shows us that. And then from here, I'm just going to I'm going to erase this so it's out of my way because I know I'm going to run out of room. I'm just going to solve for period. If I were solving for period, period would be equal to square root of 4 pi squared r cubed all over gm2. Again, just defining m2. It's not written as m2, but it's the mass of the central body. And then that's one equation, so box that equation. I'm not going to box it because I don't want to run out of room. And then I could also solve for r. Now, when we solve for r, we're going to get radius is equal to, pen quit. We're going to get a cube root, which is unusual. We haven't seen cube roots a lot. Radius is equal to cube root of big G m2 period squared all over 4 pi squared. And then I would put a box around these two because these are two equations that are helpful. Okay, moving on. Gave myself room to do that. All right, so one thing that I don't want you to do is confuse, this seems redundant and odd, but don't confuse radius of the Earth with radius of the Earth. We kind of talked about this just a second ago. One of these, radius of the Earth is, like if I am standing on the top of a mountain, here I am on the top of a mountain, the radius, they'll define radius of the Earth as the distance from the center of the Earth to the surface plus whatever the height is above that. So radius of Earth plus whatever above sea level an object is standing. So if you're standing on the top of Mount Everest, that amount above sea level plus amount above or below, we would be subtracting maybe above sea level or below sea level. And that's just our distance of the center of our body, an object standing on the Earth, from the center of the Earth to that object. Not to be confused with, although the world of AP Physics likes to squish these two things together. Radius of the Earth is the distance from the center of the sun to the center of the Earth if the Earth is orbiting around the sun. That's also called the radius of the Earth. This is the distance from center of sun to center of Earth, which is different than the distance from the center of the Earth over here to the center of our body. Kind of, but not. This obviously is much different. So the world of AP Physics likes to use these two terms interchangeably. Just be sure not to confuse the two of them because they like to call them both the radius of the Earth. The distance from the center of the Earth to an object standing on the Earth, or the distance from the center of an object. This can also be like the radius of the moon and radius of the moon. If I'm an object standing on the moon versus if I'm the Earth, a distance away from the center of the moon. So just be careful with those things. Helpful values, I feel like sometimes the book likes to just throw things in and expect you to kind of know what's going on. If you get to a problem and you're like, I definitely don't have enough information for this, come to this, go throughout the chapter of the book and find the different masses that they put in a table randomly in there. So a useful mass of the Earth right here in kilograms, a useful radius of the Earth, again, this is the distance from the center of the Earth to sea level, is this many kilometers. Obviously you want to change it to meters, and then the mass of the sun. The rest of the problems are posted for you on Schoology. so you can go through the rest of the example problems in your math packet, and hopefully that is helpful. If you have any questions about those, just let me know. All the work is posted with them.